Hi, I suppose you have already done through all the electromagnetism stuff, right, after the OC law. So this week we shall proceed with the wave, the last branch for engine physics, right. So for today, chapter 5.1, okay, all these are basically the objective that we have to cover, right. So have a read. Define wave, transverse, longitudinal. What is period, frequency, wavelength, amplitude, and how do we find speed of wave? State the speed of light. And know that visible light is actually part of the whole EM spectrum, right? And lastly, what's the difference between mechanical and electromagnetic waves, right? Okay, first thing first. What is wave? Right? This is wave. What do I mean by this? Right? When I slam on a whiteboard, you hear it. Sound is an energy, right? So, the energy goes into your ears. What is a medium that is used for this sound energy to go into your ears? Make a guess? Absolutely right. The air in the atmosphere, right? So the air as the medium, which comprise of air particles, right? So does the particle go into your ear as well, or it just vibrate? Okay. Some thoughts to begin with, right? So, if you look at this, right? Basically, waves is a disturbance that carries energy and information through matter or space without transferring matter. So to relate to this again, the air particles are just vibrating and it transfers the sound energy into your ear. Okay, so that's a very day-to-day kind of example, right? And obviously it is made of periodic motion. Transverse and longitudinal wave. Okay, for those in the know, or rather for those who have learned physics before, okay? Maybe I just want to do this in a rather different way. If you look at the screen, transverse wave. So maybe I just want to point out two things, right, that you have to know. Compare and contrast the wave direction and the particle movement direction. How do they compare? The wave is actually moving this way, right? And the particles, if you zoom in, especially those highlighted in red, the particles are actually moving up, down, while the energy gets transferred along the wave, right? Yes, they are perpendicular to each other, right? So that is transverse wave. Right, so this is another illustration of transverse wave where you see the whole plane being vibrated. Right, so let me move on to longitudinal wave. Right, if you can see over here, the screen, what is the difference now as compared to transverse? Same two parameters. The direction of the wave and the direction of the particle movement. How do they compare? If you look at the zoom-in version of the animation, the particles just vibrate to and fro, and you see the waves. Over here, they are just moving along from left to right. So yes, the two directions, how do they compare again? They are parallel to each other, right? And that is the characteristics of longitudinal wave. So at this juncture, I already covered longitudinal, transverse wave differences, and also exactly what is a wave, right? So before I move on to the next bit, I would just like you to read through, okay, the slides from page 10 right, to page 19, okay? Slide page 10 to slide 19. Okay, probably you can just spend a couple of minutes reading through for those who are not familiar with all these terms, right? Period, frequency, amplitude. Okay, for those who have already studied physics, perhaps just come along with me and look at this question over here. Right. So I'm just using this graph, the one at the top, okay, to trigger some of your memories or maybe some things that you have learned last time. Okay, if you look at this, all right, I just want you to tell me which one of these 1, 2, 3, 4 refers to the amplitude, right? Give it a thought. Is it just one? This part here, the distance, or is it the whole thing? Right? If you could recall, the amplitude is actually the maximum displacement of the particles with reference to the equilibrium position, right? Okay, for those who have read through the notes, okay, or maybe from your memory. Okay, so what do you think the answer is? It is? Yes. Answer is 1. Okay? So let me just give you one more question based on this graph over here. Okay? Look at this graph. Can you tell me what is the wavelength? Right? What is the wavelength over here? 1, 2, 3, and 4. Right? Which one of these refers to the wavelength? Perhaps you can just pause the video for a while and look at the graph. Give it a thought. Okay, welcome back. Right, so have you give it a thought? I suppose many of you will say that the answer is 4. Am I right? It's just too bad. The answer is not 4. So what is the answer exactly? What is the wavelength? It is none of the above. Hey, what's happening here? How come it's none of the above? Isn't the wavelength the complete waveform? As you have read, this is one complete wave, one complete oscillation. But hang on, I just want to point out this to you. Look at the axis. In fact, the very first thing that we give when, let's say, reading a graph is always the axis labels before you move on to the graph itself, right? So over here, if you look at this, hey, this is time axis, right? So time axis, how can this dimension being time measures wavelength, which is actually a length, right? So over here, this 4 isn't the wavelength, but it is the, think about it, what is that? The time that represents one whole oscillation is actually the period, right? So this 4 over here refers to the period. Then so how? Where can I get a wavelength from a graph? If I change these to, you're right, if I change these to displacement, okay? Right, if I change this to displacement in the x, along the x-axis of the horizontal direction, right? So this 4 becomes the wavelength. Got it? Right? So displacement versus displacement and displacement versus time graph. Okay, both look similar, but be very mindful. They are actually very different things. Right? Maybe one note before I move on. What is the key difference between the displacement time and the displacement graph? Think about it. What is the difference? Any thoughts? Right. In fact, if you allow me, let me just go back to the earlier slide on transverse wave. Right, if you look at this. over here, especially the animation at the top, right? A displacement time graph basically plot the path, okay, or the motion of one single particle. All right. So let's say if the graph over here plots displacement time, it is actually drawing the motion of one single particle only, right? But if it's talking about displacement and displacement axis, right? Over here, I'm actually taking a snapshot, right, of the waveform. That means if let's say I pause, I just take a photo, pump, right? That is actually the displacement versus displacement time. Okay, so it's all the particles that you have seen over here. Is that okay? Right, so that's the difference between these two graphs. Right. Okay, so perhaps just one more question before I move on. Right, so just now I've already covered period, wavelength, amplitude. Right, so I just want to challenge you a little bit more. If you look at this graph over here, right, the bottom graph, hey, wow, this is not the type of graph that you have seen, the normal sine graph, right? So you look at this, same thing. What is the first thing that you check? Once again, if I give you the graph, right, obviously you look at the axis first. There you go, right? You are learning. Okay, so displacement time. So displacement time, question, does it give me wavelength or does it give me period? Think about it, right? Okay, so now look at this. The first question would be, right, what is the amplitude of this waveform? Right, you can pause over here, look at the graph again, tell me the answer. Right? What is the amplitude? Is it 4? Is it 5? Which one is it? Right? Or is it none of the above again, like the trick question I gave you earlier on? The amplitude would be, think of the definition, right? If you chose this, you're right. Okay? It is basically option 5, right? Because it is the particle, or rather the displacement the particle goes through from rest position to the maximum displacement. So the maximum displacement is actually here and here, right? So this will be the amplitude, right? So the next question would be, what is the period of this waveform? Is it 1? Is it 2? Or is it 3? Give it a thought. What would it be? Remember, what is the period? It is for the whole complete oscillation. So if you look at this part over here, the graph, is this one complete oscillation? And then over here, is this one complete oscillation? Or is it this part is one complete oscillation, if you look at the graph, right? Basically, to me, how would I explain is, one complete oscillation basically is this. If I could just take this part of the graph, cut and paste it next to it, adjacent to it, and the graph looks like whatever that's given, then that would be the complete oscillation, which is 3 representing the period. With me? Right, because if I cut and paste this part, obviously I'm not getting the given waveform. If I cut and paste this next to it, I'm not getting the original waveform as well. Right? Okay, just perhaps one more thing before I move on to how do you calculate speed of the wave, which is the most important equation, right, in wave. I just want to highlight one thing. If you look at your slides, over here, there's one term in phase. I just want to briefly talk about this. Yes, the definition is here. right? Particles of the same phase basically are the same displacement from equilibrium, at the same time moving in the same direction, right? I think it's better for me to illustrate using some animation as well, right? Exactly, where is the particles in phase with each other? I'm just going to go back to the same animation that I showed you just now, over here. If you look at the screen, which of the red particles are in phase with each other? Right? If you look at this, this is 1, 2, 3, 4, 5. So which one are in phase, right? Remember just now the definition of in phase, right? Basically means that they are at the same displacement from the equilibrium position, okay, and moving in the same direction at one particular instant, right? So if you look at this particle and this particle, are they in phase? I suppose hardly, right? Because over here it's moving down, then after that it's moving up, right? You can see that it's not together. How about this particle, particle 1 and particle 3? Are they the same? I don't think so again, right? Then how about particle 1 and particle 4? This particle and this particle. Can you see? They are moving down, up, down at the same time, right? So these two particles are basically in phase with each other, right? You refer back to the definition again in the slides, right? Okay, so maybe just tie this into the definition of wavelength or period, right? Because in your slides, just now it mentioned the two successive particles that are in phase with each other, the distance between these two particles in phase is defined as the wavelength. Over here, these two particles, are they the successive particles in phase with each other? No, right? Can you see that? Where's the next particle that's in phase with this particle 1? It is actually over here, if you can see. Right? Let me just catch. Right, over here. Can you see that? These two are actually the two particles that are successive and they are in phase with each other. Right? That means directly next to each other and they are in phase. Right? Okay. So, I'm done with all this period, wavelength, amplitude. Okay, one more. Frequency. What do you mean by frequency? Right? I think in English, usually frequency means how often. Right? How often. So, in the wave context, right, frequency, what do you mean? Make a guess. Means in 1 unit time. Basically, how many complete waves have occurred, right? So, based on your understanding of mathematics, I can actually use period to calculate frequency, right? So, let me just quickly move on to the formula for frequency that relates to period. Yep, F equals to 1 over T. And T is the period, F obviously is a frequency. The unit for frequency is hertz. Right. How do you spell hertz? Frequency, Hz in short, or Hertz. Right? Okay, so let me just move on to the most important wave equation. Right? Wave equation. Right? Over here, you can see at the bottom. Just remember this. V equals to F lambda or C equals to F lambda, whichever, right? V, speed of the wave. F, you have already learned, frequency. Lambda is basically it's a short form or the symbol that represents wavelength, right? Over here, look at the questions, right? These 3 questions. If you look at the graph, displacement, distance, right? Or displacement, whichever. Right? So displacement, distance graph. bear that in mind, what I said earlier. What is a wavelength? Can this graph give me the wavelength? If yes, how do I read it? Period of the wave. Aha, period of the wave. How come I have to give you? Because it's displacement distance, right? Okay? To read the period, I have to give you displacement time. Right? So what is frequency and speed? Based on this, how do you calculate? Right? Lastly, what is the wavelength of the wave if this frequency is increased to 5 Hertz, right? With no change in speed. Meaning, the answer that you found in part 2, in question 2, the speed remains the same. Frequency increased, right, to 5 Hertz. What is the wavelength? What do I use? Right? Give yourself probably just 1 minute or 2, work out the details, right? And we'll talk about it. Okay, welcome back. So if you look at the question again, wavelength, right? Wavelength basically means that the complete oscillation. So if I look at here, the complete oscillation would be until here. So the wavelength is actually 50 cm, right? From here to here, or you can choose to refer to here to here. But the problem is over here, there isn't any clear values. So the preference would be from here, 0 to 50, or perhaps 25 to 75. Then you take the difference, right? 50 cm. Okay, the period is 1 second. What is the frequency? The formula for frequency and period is actually F equals to 1 over T, right? So the period is 1 second. Obviously, the frequency would be 1 divided by 1 second equals to 1 Hertz. Okay, so that's the frequency. And how do I find the speed? V equals to F lambda, right? So frequency is actually 1 Hertz. Lambda, wavelength is actually 50 cm, right? 50 cm. So the answer is 50 cm per second. Do take note of the units, right? Do take note of the units because the wavelength is actually in cm. So please don't write meter per second, right? So this is part 2. Okay, the last one, part 3. How do you get 10 cm? Same thing, the most important equation again, right? So now, the question said, hey, the frequency is increased to 5 Hertz, right? Frequency increased to 5 Hertz. Speed is still the same. Ask you to find the wavelength, right? So I just adjust this equation and I make wavelength the subject, right? So it's V over F. The speed remains the same, 50 cm per second over, frequency would be 5 Hertz. Then, what is the units? Make a guess. Yes, cm. Right, there you go. Okay, I think one thing about the wavelength, the usual way of identifying the wavelength is not there, right? It's like, hey, you say that, hey, I want to take from here to here. That's usually how you identify the wavelength. Can you all see that? Usually, hey, I identify from here. But this is not a good way. Why? Why this isn't a good way? Because usually I say, hey, I identify the whole wave like that, from equilibrium, then go down, come up, then hey, go back to here. Please don't assume. Okay? The key thing is that when you're given a graph, the numbers are not there, don't assume. Okay? Right? So you take the next better option, which is from crest to the next available crest. Okay? Or the trough to the next trough. Okay? Because I have the values over there. So wavelength 50 cm, period 1 second, frequency and speed. The only thing I want to bring to your attention is the units. Okay, be very mindful of the unit cm. The speed will be cm per second. Okay, even though I say over here, I can foresee that some of you will fall into this trap. Okay, because you are so used to meter per second, and sometimes you are very fast. Okay, right? So 50 cm per second. Right. Okay, so if not, basically I've already wrapped up the key points for waves. I mean the calculation part, certain key parts of the wave, right? Okay, so the next few bits, right? Okay, this one state the speed of light. What is the speed of light?
3 times 10 power 8 meter per second.
What is the speed of light? I heard you. 3 times 10 to the power of 8 meter per second. Okay? Right. But one thing I just want to get you all to have, because physics, sometimes we learn, right? We must have that feel. So 3 times 10 to the power of 8 meter per second. How fast is that?
Super fast.
Super fast, right? If I could get you all to convert it to kilometer, what would that be? 3 times 10 to the power of 8. Convert to kilometer. 3 times 10 to the power of 5, which is, what is the value? 30,000? 300,000, right? 300,000 kilometer per second. How fast is that? How big is Singapore?
60 km.
I mean the width of Singapore.
About 700 kilometer.
Singapore, the width is 700 kilometers.
No, that's the area. I say area. 42 kilometer.
Yeah, it's only 42 of
Okay, from Tuas
I say area.
to Pasir Ris, I mean end to end, probably maximum 50 kilometers. That's about it. Okay, right. So how many times can light travel? I mean, in 1 second, 300,000 kilometers. 1 second. Okay, so you get that feel, right? Okay, so let me just move on. Electromagnetic spectrum or waves. Okay, it just to make some sense out of this. Okay, right? For waves, listen. Okay, I was just thinking about it earlier on. How to make things flow better for all of you. Okay, so for waves, usually we classify them transverse, longitudinal. Okay, there's another way to classify waves as well, which I don't think many of us think it that way. It can be classified or categorized as EM wave and mechanical. Okay, what is the difference? What is the difference between mechanical and EM wave, which is electromagnetic waves? Mechanical wave, right? Actually, I'm jumping the order a little bit because I thought it is appropriate to introduce it now. Okay, so if you think of mechanical waves, right? Basically, they are waves that requires a medium. What does it mean? What is a medium? What is a medium? Basically, it is a matter, M-A-T-T-E-R. Okay, either solid, liquid, or gas. Right? Sound. Is it a mechanical or electromagnetic wave?
Mechanical.
Mechanical, right? What kind of medium does sound ride on? The medium for sound, air. Right. Imagine if I have this super huge pump that suck out the air from this room. Then I'll be like that.
You cannot hear.
Okay? Right. So, sound, right? In fact, we have so many demonstrations. Actually, you can see at the very last bit, there's this QR code. You can go and scan it. Okay, look at the demonstration. It's a vacuum jar. Suck out the air, then you can put a handphone inside. From ringing, after you can see the handphone vibrating only, but there's no sound. Okay, I can do that in the lab as well. If y'all want to see, right? That time I use my handphone, I take a risk, I put my handphone in. I thought, maybe the handphone would get distorted or what. Okay, mechanical basically requires a secondary medium. Okay, the rope, the slinky coil, mechanical wave. Light, is it Mechanical wave? Light. Or is light a wave at all? Huh? Is it a wave? Yes, okay. Light is a special kind of wave, okay. Right. So anyway, okay, EM wave, Okay, some of you're very experienced with this. Y'all know that, hey, wow, there's a song or whatever. If you're interested, you can go and play the song. I'm not going to play the song here. Okay, so the other way to remember this, Ronald McDonald, okay, another crack, is very ugly. Except Gary lah. I also don't know why lah. I mean, sometimes a bit. Okay, Ronald McDonald is very ugly except Gary. Hey, really, I use that to remember since my secondary school days. Okay, so first thing first, right? Okay, first thing first, all the components. Okay, please, using whatever way that is good for you. All right, the next thing is, which one among all the EM wave has the, or rather have the highest energy? What do you think? Okay, a clue, right, over here. Okay, over here is a wavelength, right? Wavelength. What is the speed of electromagnetic waves? All electromagnetic waves travels at the speed of light, okay? All right, so all components, right? So if the wavelength is very small, the frequency will be very high, right? Using, what thing? Speed of light. All electromagnetic waves travels at the speed of light. No, not sound. Okay? Right, unless it's ultrasound. Ultrasound is a different thing. Right, so speed of light. If speed is the same, V equals to F lambda, the smaller the wavelength, the bigger the frequency. Alright, so is gamma ray having highest energy or is it radio wave having highest energy? You think about it, frequency. If very high frequency compared to something that's very low frequency, which one have higher energy? You think about it. Use your feel. Frequency very high. Wow, something that move rapidly. Then compared to one particle that move.
Sounds like me when I wake up in the morning.
Right. I mean, you can feel for it rather than memorize, right? So, this fella here has the highest energy. That's why what is gamma rays used for? Kill cancer cells, chemotherapy. Right, that's why people who went through chemotherapy, what happens to them? Lose hair, I mean even the facial hair. Right, because the energy is so intense. I mean even destroy
all the cells.
The cells, precisely. Right. Imagine, hey, let me tell you something very scary. If you think that radio wave has the highest energy, where can you find radio waves? Everywhere. If radio waves has the highest energy and is found everywhere, all of us will be dead by now.
Yes.
All of us will be dead. Yeah, precisely. Okay, so that is one way for you to remember in terms of energy. Right, so the key thing, okay, visible light is the smallest spectrum in the whole EM wave. Okay, I just need you all to, okay, this one, no other way, you all have to memorize this wavelength for visible light. Okay? Violet, red. Okay? What is the wavelength? Alright, from 400 nanometer to 700 nanometer. Okay, you all have to memorize. But I can share with you how to remember which is which. That means 400 nanometer, is it violet or is it red? Okay, how I remember, okay? You want me to share with you? Okay, red gives you the feeling of hot or cold. Hot, right? Hot gives you the feeling expands or contract. Hot expands, so it is a longer wavelength. On the other side, blue gives you the feeling that, it's very cool. Right, icy cool. Blue color, sky blue. Right, very cool. Right, so contract, shorter wavelength, 400 nanometer. Okay, that's how I remember. Right, so basically this one gives you the exact wavelength, okay, or rather the range of wavelength compared to the energy. Just now I already shared with you, The smaller the wavelength, the higher the energy. EV is just basically a unit of energy for particle level, right? All okay? Road wave, all this, you all can just do it on your own. Okay, sound I already mentioned. The QR code is there, right? Okay, can I end this part by showing you a concept map okay, that I draw just now, right? So first thing I covered, what? Okay, hope that you still remember what is a wave. All right, then after that I share with you the types. Okay, there are two ways we can categorize. First is A, particle to wave direction method, which leads to parallel and perpendicular. Parallel is longitudinal, perpendicular is transverse, right? And whether a medium is needed, then it branches out to two types. Then EM wave, obviously the Ronald McDonald story, okay? Right, so the types. Then the last one, obviously, is the properties, right? So the properties of wave, all these terms you need to know, right? Okay, period, frequency, lambda. Okay, so amplitude, speed, wave equation, right? So basically that's it, okay? Can?